Professor Kim is an assistant professor in the mechanical and the industrial engineering department at the University of Illinois at Chicago, and so she received her PhD from our Carnegie Mellon under Professor Steve Collins, and then she worked as a postdoctoral researcher at Harvard before joining USC. And Myunghee, the floor is yours.
Yeah, thank you. Thank you for this opportunity. So today, I give a talk with the title of Human Robot Co-adaptation. So basically, our lab is trying to how to best use the robot, also how to guide the user to use the robot, considering we have really limited power, with a collaboration with lots of high-profile professors. So I think this group already know that there are lots of individuals with reduced mobility, and then they often experience increased cost of working. And then one of the measure of measuring the cost of working is the metabolic cost using this one mask. And some like the amputees, if they wear the passive device, they presented 25% higher metabolic cost to travel the same distance compared to able-bodied counterparts. So 25% is approximately maybe carrying 10 laptops at the same time. And for me, I have a 6-year-old boy who I need to carry the boy at the time, which I really did not want to. So yeah, that is the cost they are carrying. So of course, one of the approach could be using robotics technology and applying the active active device. However, it's not as easy, maybe as we thought. It's mainly due to unknown human-robot interaction. So this subject were called ankle prosthesis emulator using this simulator boot. And we also made, the researchers, not myself, measured the metabolic cost. And then the hypothesis was that if we provide more energy from the device, the subject can reduce more metabolic cost. So in some cases it worked, but actually these researchers tested the idea with actual amputees. They didn't see any trend. So even if we they changed it, we provided lots of energy, the metabolic cost remained almost the same. So like, why is this happening? And how can we address this challenge? So my approach has been using computational and hardware, including human in the loop. So I have used simulation study, and then I developed a control idea how to develop assistance method, and then tested with simulated amputees and then actual amputees. And then at that time, we developed a control idea to assist the balance. And we found that the simulated amputees reduced the metabolic cost of working for the stabilizing controller condition compared to the neutral condition. Also, at the same time, they reduced called maybe hip control effort shown by step reduced variability. They reduced about 10% metabolic cost. This time, we also saw similar metabolic cost reduction for the amputees, and also they reduced this intent limb control effort. So it seems like so using this human approach, we were able to develop an assistance method to improve balance. However, now I want to draw your attention to this high standard deviation bar. Means that there was a subject, actually we did great, who reduced 25% metabolic cost. But there's another subject who actually increased metabolic cost. So we really gave a disturbance. We gave a really hard time to a subject. So we were thinking, why is this happening? So the hypothesis was that the response curve will be different depending on the subject. So this x-axis shows a control parameter, and the y-axis shows called metabolic cost. And then this is a response curve from maybe subject A, and this shows a response curve of the subject B. And actually, I draw this plot using collected data. So therefore, this is really happening. So it means that maybe the optimal parameter for the person A can be something like this. The optimal parameter means the metabolic minimum parameter for the person B will be something like this. And if we apply the same parameter to this person, the person will actually increase metabolic cost. So it means that we need to somehow tune the control parameters in a smart way. So one of the methods is called human in the loop optimization. So we developed a called human in the loop optimization to optimize parameters of the called hip exosuit, which is a textile-based exoskeleton. And we collected metabolic rate in real time and used the information to optimize called peak and offset timing. So in a real time, what happens is that we collected the data and then we fit the data to a curve and then select the next parameter and then provide assistance to a subject. As a result, we saw about 17% reduction for the optimal condition compared to no device condition. And as we expected, we saw a wide range of parameters. So peak timing for the subject 6 was a bit early, but the peak timing for the subject 4 was very late. And therefore, the optimal assistance profile was very different. Importantly, the metabolic cost reduction was also very consistent across subjects, shown by this small standard deviation. Also, we found the optimal condition within 20 minutes. In a conventional method, it could take about 2 hours. But this 2 hours, 20 minutes is still a little bit slow if we are considering applying this method to physically intensive activities such as squatting, or for individuals with impaired mobilities. So we developed a fast optimization method, and it was already presented by Prikat and Michael. So please check the talk if you missed the talk. Also, eventually we want to optimize assistance for individuals with reduced mobility, such as amputees. So as a first step, we tested whether this human optimization, personalized assistance, can optimize assistance even for simulated amputation first. So we optimized the parameter of the ankle foot prosthesis using metabolic rate. So what happens is that we collected a metabolic rate in real time, calculated the cost, and then we selected the next parameter, and we were able to find the best parameter for 2 subjects. And then the best parameter reduced metabolic cost of working for both subjects. Seems like this human in the loop optimization in ankle foot prosthesis seems to working. Then, of course, we wanted to test 2 individuals with amputation. So like the amputation, this amputee had only 1 day of training, but second day we did optimization, and both of them were able to reduce metabolic cost of working compared to baseline condition. So now I move on to the alternative cost function we are pursuing. So far, we did called human optimization using respiratory measure, which is very cumbersome. You can't ask to wear this mask all the time for a subject. Also, it takes a long time to estimate the cost. So we are searching for an alternative measure, and one candidate is foot pressure symmetry. So we found very good correlation between metabolic cost and foot pressure symmetry. And therefore, we try to use this foot pressure symmetry to optimize assistance. So basically, we did human optimization with a cost function using foot pressure symmetry. And we found that the 6 subjects were able to reduce the metabolic cost of working compared to baseline condition in 10 minutes. So it seems like foot pressure symmetry can be a cost function to optimize assistance. So next, we are also trying to optimize assistance for amputees as well. So in this case, we are trying to use socket interface pressure. And for this case, for the amputees, we were also able to observe reduction in metabolic rate for the optimized assistance compared to baseline condition for both of the subjects. And this is also a clinical measure called a Borg scale perceived exertion. The subject, so the lower number is better. And then especially subject 1, he reduced, the number was was lower compared to weight-based condition. And he even liked our device compared to his unprescribed device. This is very unusual. So far, I talked about how we can address this challenge, how we can address this inter-subject variability. But another thought we have in mind is that somehow this works for similar to the amputees, but it didn't work. So even the generic assistance didn't work for amputees. And why is this happening? So one thought was it's because amputees need to forget how to use their device and they relearn how to use the new device. It is similar to if you are the Mac user, if you are using Windows, you need to forget how to use the Mac and then we need to relearn Windows. It may be harder than just learn Windows in the beginning. So like maybe we need to guide the use of the wearable robot. And then if you think about the other assistive device, even the very simple cane, there's a handbook how to use the cane. So for example, like maybe for the first, if you have a sprained ankle, and then in the beginning, you might think that you may have a cane in the affected side, but actually it's wrong. You need to have the cane in the sound limb side. But at least our lab, for the robotic device, something like this very complicated device, we just provide the device to a subject and they let them work and hoping that they can figure out how to use the device. So the hypothesis was that where we want to provide user guidance to best to use the this robotic ankle foot orthosis. So we made hypothesis that if we provide the training, it may reduce the effort, even called metabolic worst condition, which initially provide purely disturbance to a subject, which made the subject harder to work. And then the training will help to maintain effort for the called metabolic best condition, which is considered personalized assistance, one of the best assistance. So we provide the training using visual feedback. So basically, this subject where this ankle foot orthosis, we measured the torque difference, and depending on the torque difference, we gave feedback that you need to move your toe to up, or you need to move your toe downside. And then we measured the pupil diameter using eye tracker, one of the measure of cognitive load and the metabolic cost, and also muscle activity. So this is overall experimental protocol and the result at the same time. So we provided 3 different stiffness conditions, and we selected personalized metabolic worst condition, means that this condition increased metabolic cost compared to the baseline. Also, we selected personalized metabolic best condition, means that the condition decreased metabolic cost compared to baseline. And then the subject experienced visual guidance training for 6 minutes. And then we measured the metabolic cost of the pre-training metabolic worst condition and the pre-training metabolic best condition. So for the pre-training metabolic worst condition, which was really hard to work in the beginning, now after the training, now it's easy to work. So the subject was able to reduce metabolic cost compared to the baseline condition. And then the subject was able to maintain metabolic cost for the best condition. So they didn't forget how to use the device. The soleus muscle activity was dramatically decreased after visual guidance training for both of metabolic worst and the metabolic best condition. But there was a cost. So it seems like this visual guidance training made the subject how to do the device consciously. So it seems like the subject seems to increase the pupil diameter, meaning that they need to focus more on maybe they need to use their mental source a little bit more, especially for the metabolic worst condition. Metabolic best condition, which was easy to work in the beginning, there seems to be a trend, but it wasn't statistically significant. So it seems like there's a very big component how to use the device, how to use the robotic device. So maybe the metabolic worst condition is not necessarily mean that it's not like a really bad condition. It means that the subject doesn't know how to use the device. So far, I talked about how to tune the robot or optimize the robot to best assist the user, and how to make a user guidance to best use of the robot. The question is how we can facilitate this robot user co-adaptation. This is our ongoing research. Our labs to keep thinking about how we can make this methodology. I'm very happy to discuss about this idea. With that, thank you for your attention, and thank you for listening. I hope that I am on time, and thank you for the sponsors. And importantly, I'm looking for postdoctoral fellow and research staff. So if you have interest in, feel free to reach out.